something, then it's good work for me. I am justifying my job. Otherwise, it's not done properly. But of course, the participation should be from your side as well. Okay, so as of now, 93 people, including me. Okay, fine. So today is lecture 9 for this course EN 203, Digital Electronics and Circuits. And we are seeing many ways to fabricate or design the gates practically. And that's what we have been doing through different logics, let's say diode logic, or you can also say resistor diode logic. Then we came to some resistor transistor logic. So these are some of the things through which we are trying to realize some or the other gates. So this RTL we have seen last time, how we realize the NOT gate. And then we have also seen that how can we design R1 and R2 so that the transistor behaves in the manner in which we want. So that is the ultimate purpose. If you can make it behave according to your requirement, then it is fine. Your circuit will work fine for all the conditions. So we have seen that what should be the values of R1 and R2, how should we choose that, so that even for the worst input, so worst possible input, I mean the lowest range for the highest, the lowest range for the high input. So if you are saying 2 volts to 5 volts, the lowest voltage would be 2 volts. So up to this, the circuit should operate perfectly fine. So that is the purpose of designing. And we have seen that, okay, if we are saying that R1, say assuming that is 2 kilo ohm, because which is what is giving reasonable value of current, collector current, then our R2 or the base resistor should be something like, what we have got, some of the range of 5 kilo ohm. So anything around 5 kilo ohm is fine. 4.8 or 5.2, something is fine. So knowing that how the conditions may vary and what may happen. So this was one of the assumption which we got in the beginning, that R1 should be high and R2 should be low. So we see that, I mean, what looks correct may not be. Actually here R2 is high and R1 is low. So may not be true always what we perceive directly, but yes, getting or having some idea about the circuit or the starting point is a very good thing. So then we have seen the performance of this NOT gate, how it would behave with the input, how the output would be. So there is some transition phase which we are calling undefined, and before that we have the high state for the output whenever the input is low, and whenever the input is high, the output is low. Basically VC SAT value or VZ. So this is what we have seen, and then we try to realize some NAND gate, then NOR gate. So okay, this one was the inverted OR. So this was NOR gate. So based on what output it is giving, we can say like what configuration this is. So that was NOR gate. Then we have seen the NAND gate configuration also. So something like this, using the DTL, diode transistor logic, we can configure this kind of gates. So essentially these are the basic building blocks for the more sophisticated and more advanced logic designs, and somewhere we are utilizing these basic concepts only, but the shortcomings what we are getting in these circuits, we are trying to resolve in the next version, and we are coming up with the better technology for the design. Now, what problem could be there with this RTL logic or this DTL logic, whatever we say, with all this, what problem could be there? That is what we will try to see, and then we will try to come up with something more better, something more advanced and more universal, we can also say, because these things are ever evolving, and lot of people have been doing research and all this to continuously improve the performance and the characteristic of the circuits. Now, let us see what problem do we have if we are saying that, okay, we have the RTL inverter. what problem could be there? So any guess can you make? What could be the problem with the circuit? Then only we need to go for something better. Let's say I draw the circuit. Here we have V in, here we have V out. So what could be the problem? Let's say we have designed R1 and R2 properly. So transistor is getting biased in the saturation or cutoff mode and it's working fine. But what could be the problem? What could be the possible problem? Any guess? Can you make? This is fine. People would have been operating with RTL itself forever, but they did observe some problems and they found that there are some shortcomings in this circuit which is not possible to resolve at this level. We need to go for the next one. So can you guess what could be the problem? Okay, I give you some hint. Let us try to put the equivalent circuit in off and on mode. So let us say in the cutoff mode, how the transistor would behave.
Open circuit.
It's open circuit. So this is the gate and you are not giving anything over here, no? Vin is equal to 0. VCC is there, some R1 is there, and then you are having the out. It is fine. But ultimately this has to drive some load, isn't it? Yes or no?
Yes.
Now, what is this output? If you say the V out voltage, what would you write?
RL.
VCC into RL upon RL plus R1.
Isn't it? Now, assume that this RL sometimes may be comparable to R1. It could be, right. Sometimes the load value, load resistance value could be lower. Sometimes it could be higher. So by lower and higher, what I mean, let us say it could be something like few hundred ohms, or it could be few kilo ohm, or it could be in the range of 10 kilo ohm. No, these are all possibilities. We may have different loading conditions. Now, what will happen to this out? If let us say RL is large compared to R1. If RL is very, very large compared to R1, then what will happen?
V out near to
V out would be very, very close to VCC. No problem. There is no issue at all. But in the other condition, when R2 is comparable or less than R1, then what happens? Your V out is dictated by your R1, isn't it? Let's say R1, sorry, this is RL, not R2. Let's say RL is equal to R1. Now your V out would be what? VCC by 2. Isn't it? Say your R1 is equal to some 4 times of RL. Now your V out would be what?
VCC by 5.
Isn't it? Yes or no? Yes. So what is happening? Your output for the same input is being dictated by what is the load resistance over here. And that's not a good thing. For a better circuit design, you don't want this kind of behavior. This is a very, very nasty behavior where your output is determined by what load you are putting. Now, who would know that what someone is going to connect to that IC? How would you ensure that? Then you have to specify that, okay, you cannot connect any load value less than this. Isn't it? So you are somewhere restricting the usage of this circuit. Further, Let us see what happens in the saturation mode, keeping this condition what we have drawn over here. So what we can say that if we are keeping R1 value low, then our circuit is going to behave well in the cutoff zone or the saturation zone, isn't it? If you keep R1 value very low and assuming that the load is not going to go beyond something like, let's say, kilo ohm, then it is fine. It will behave properly. Now what will happen when you go in saturation mode? So what is the equivalent circuit in saturation mode?
Short circuit.
It's VCE sat. So here you are giving V in equal to 1 and you are trying to take this V out. Now what will happen to this collector current IC? Your IC is very much closer to VCC by R1. Now if you apply the same condition, if you apply R1 value as very low, ICC will be I collector current would be very high, isn't it? So what will happen? Then accordingly you need to adjust your base resistance. You need to pump much more current in the base to have the condition fulfilled for saturation state. So what this saturation state is saying that R1 should be reasonably high as well. So these two conditions are contradicting each other. One is saying that R1 should be low for correct behavior of the circuit for different loading conditions. Another is saying that R1 should be high so that you don't pump too much current in the transistor. And secondly, you don't have to have very low value of R2 or don't need to pump so much current in the base as well. Understanding my point? Yes or no?
Yes, sir.
Yes, sir.
So these two conditions, the cutoff mode and saturation mode. What the first condition is saying that R1 should be high, the R1 should be low for the proper circuit behavior. And here it is saying the R1 should be low again. Correct? So how to manage between the two contradictory situations? Any suggestions? What can we do? How to handle these contradictory situations? Again, keep your camera on. Don't turn it off in between. Any suggestions?
Sir, a diode which is on in cutoff region and off in saturation.
Okay, so what that will do?
So in the cutoff region, if it is followed by, then the R1 will be low and
Something like this. Something like this.
yes, sir.
So what will happen? When it is conducting, it is conducting. When it is blocking, still it will be conducting. So diode will always be forward biased.
Yes, sir.
See, you are the future designers, no? You have to think from design point of view. What can be done? Think about it. These things have not come up overnight. No, a lot of people have invested lot of time, lot of energy, lot of research has gone into this. Many PhD theses or research papers must have come out of all these things. Think about the problem, think about the solution. I would really appreciate if some of you can really suggest something. What can be done? Yes? Okay, I give you a hint. See, this is where now we go into transistor logic. No, this is called TTL. says that why don't you manage this resistance problem with another transistor? See, we know that when transistor is in cutoff zone, it is equivalent to very high impedance. And when it is conducting, it is equivalent to short circuit, almost, or a very small EMF over there. Isn't it? Yes or no? So
Yes,
somehow, if you can have two transistors working in opposite modes, let us say something like this, and somehow you manage to give the complementary inputs to these transistors. Let's say you are giving some input A, then you give A dash over here, and you try to connect any load. So of course we cannot have bare transistor connected, so we can connect a small resistance over here. Let's say some R equal to the standard for TTL, they take 130 ohm. Let's say this is the resistance that is connected, and this is the load V out over here. Now what will happen? When the input A is equal to 1, so this transistor is on, whereas this is off. Getting my point? So what will happen? The load will be driven like this, and V out will be what? This will be high. But because this R is 130 ohm, which is very, very insignificant compared to whatever typical load resistance we put, maybe some 1 kilo ohm up to 10 kilo ohm, let us say. So then this is insignificant, which means this is not going to be dependent on the load resistance. Your R is very, very less than RL. So V out is going to be very, very close to VCC. Isn't it? Yes or no? Second condition, yes or no? Understood or not?
Yes, sir.
Yes, sir.
Now second condition, if you give A equal to 0, so what will happen? This will be off and this will be on. Now your current will flow like this, and only the VC sat voltage over here will be applied across the load, which means the V out would be 0 or low state. And this resistance is not small because this is going into off mode, which means this is not drawing very high current as well. Understanding my point? Now there are other ways how this transistor will be biased and this transistor will be biased, but more or less this kind of structure we are looking for. So we are putting two transistors on top of each other which are acting in opposite mode. So this kind of structure is basically called totem pole. Totem pole structure. Understanding my point? Yes or no? Now using this we can resolve the problem what we were facing in the resistor transistor logic. Of course, this is not used as it is. What we do, we make some other modification also. What modification we make? We put a diode as well, but not for that purpose what was suggested. This has a different purpose, which I will discuss later on. So this is the kind of structure which is used. This R value is still 130 ohm. Understanding my point? Now how to drive this circuit? It is okay if we can drive, the condition was that, but how to drive? So again, after lot of thinking and research and all these things, they have come up with a very simple structure which you can draw like this. So you can connect this terminal over here and this terminal over here. So let's say R1 and R2. See, these R1, R2 are these things we will be changing, no, depending on when we are going to full circuit or we are including more components. So this count you don't try to remember, only you try to remember the configuration. Now this R1 is something of the order of 1.6 kilo ohm. That is the standard TTL value what is considered, and this is something like 1 kilo ohm. Now what happens? Let us say this is Q1, this is Q2, this is Q3. Now let's say we are giving input over here. So of course, depending on the condition whether this is going on or off, it will drive one of the transistors in on or off mode. Understanding my point? Yes or no?
Yes, sir.
Now let us say this transistor is going into off mode. So first condition I take when Q1 is off. How it is off, what is happening, we will see later. But first let us say the driving circuit, this Q1 is off. So what will happen? What will be the voltage at this point? Yes, keep saying.
Almost VCC.
Almost VCC.
Almost VCC will be here, isn't it? Because this path is not conducting. So your current will try to take this path because this voltage is higher. So it will bias this transistor Q1 in on mode. And the current will take this path. Isn't it? The base current and then this collector current. So this would be the typical path for the current. Now, if this is on, what will be the voltage over here at this point?
VCC minus 1 B out.
So you see two diode drops over here, right? So VCC is at this point, then this is 0.6 volt, then this is 0.6 volt. So how much is the voltage at this point?
VCC minus 1.2.
Something like 3.8 volts, isn't it? See, 0.6 and 0.6 are dropped out, right? What is remaining over here? Say something, yes or no. Here it's important for you to understand and respond.
Yes, sir.
Getting my point? So obviously this is driving this output in high mode whenever this input, this transistor is off. Understanding my point? Now,
Yes.
the only thing to understand is that this voltage, you see, it is not dependent on RL, but it is dependent on the two diode drops subtracted from the actual voltage, the applied voltage. Maybe some more because current is flowing, so it may be slightly lesser, let us say 4.8 volts. So then another 0.2 volts may come down and 3.6 or 3.4, but still it is in high mode. Correct? Yes? So this is how the circuit is driving this transistor to go into on mode and obviously this into off mode. There is no voltage to drive this. So we are getting this output over here. Now, taking the second condition, let us say, so, okay, let me draw another circuit to avoid any confusion. You must understand that this is something which has not come up overnight. So we have to understand it slowly, but the understanding should be formed. How it is happening, what is happening, and let me copy this circuit for saving time. Okay, so this is what we have. Now let us say that this transistor is driven into on mode. So Q1, Q2, Q3. Now Q1 is on. Somehow we are making this transistor go into on mode, which means what is the drop across this? This is VCE SAT, something like 0.2. Clear? Now what will happen? The current will be flowing in this manner. No, it will flow like this. So what will happen? Yes, of course, there is possibility that these both voltages could be high and high enough to drive both the transistors in on mode. So let us say what happens when this transistor Q3 turns on. So if Q3 is on immediately, so there will be some current flowing like this, isn't it? So what will be the drop across this base emitter junction?
0.6.
0.7 volt or 0.6 volt, whatever you want to say. Okay, now the moment this Q3 is driven and it is on, this 0.6 volt appears across R2. And then on top of this, we are adding 0.2 volt because this Q1 is also driven into saturation mode. So then what is the voltage at this point?
0.8.
0.8 volt. Now, is this voltage sufficient to drive Q2 in on mode? Yes, if this diode had not been there, any voltage greater than this junction threshold 0.6 could have been able to drive this transistor into on mode or in at least linear mode. But when we are having this diode, what it gives, that it needs another additional 0.6 volts on top of this for making this transistor in the saturation mode. So now the required voltage at this point should be at least 1.2 volt for making this transistor Q2 into on mode, which is not there. It's hardly 0.8 volt over here. So then what would be Q2 at this point now?
Off.
It will be off. The voltage is not sufficient. Understanding my point? So we are automatically getting this kind of configuration what we had thought of earlier. So when Q3 is on, Q2 is automatically going into off mode because the voltages which are appearing are not sufficient to drive Q2 into saturation mode. So that was the purpose of this diode. When we are keeping it here, we want additional 0.6 volt threshold to be added for this transistor. So then whatever we make, whatever amount of current we draw, whatever we do, this voltage is never going to cross 0.8 or 0.9 or maybe max 1 volt. Even if we take VC saturation 0.3, diode drop as 0.7, it's never going to cross 1. So then this is never going to turn on as long as this is on or this is on. Am I clear?
Yes, sir.
Yes or no?
Yes, sir.
So now what is the value of output over here? When this is on, what is the value of output?
Point 0.2.
Yes. That's the voltage across this resistance, right? VC SAT, that's all. So by default, irrespective of the load. The moment this transistor conducts, this is at 0.2, which means low, irrespective of what is load. So that is the advantage of this TTL technology, transistor logic. The outputs are not driven by what load we are putting. It is driven by what circuit configuration we have internally. So the drops across the transistor, diode and all these things, these are dictating what output voltage will appear over here for the given VCC. Understanding my point? Yes or no?
Yes, sir.
So we have seen these two conditions, but this is not all for transistor logic. We still have not figured out what is happening to this transistor, what is happening to this input. Can we simply have resistance and drive this? Okay, we can do that, but there is something better that can be done. So what better can be done? Another speciality of this transistor logic is we can have multiple inputs driving this complete circuit and without any additional much difficulty. So what we can have a transistor which is used in this form. Where the base is driven by this VCC, and this is where we are connecting our input. Now how we can add more inputs, I will come to that, but first let us see what is happening here. So you can consider that for general crude understanding that this transistor can be seen as two back-to-back connected diodes. Something like this, where you are connecting your VCC, something like this. One is connected to the input, and another is driving this transistor. So let us name now again. Once again, we are putting now additional some components are there. So we will put some name. Let's say this is R1, Q1, R2, Q2, R3, R4, Q3, Q4. This diode D2. Why D2? Because we will have another diode over here for some purpose that I call as D1. Okay, I will come to the purpose of this diode, but first let us try to understand this, what is happening over here. Let us say when you have the transistor in this configuration, the base emitter junction and this base collector junction, this can be driven by this VCC voltage over here, depending on what is the input given. Let us say this input is 0. You are giving 0 input. So what will happen? Your base emitter, this junction will be broken and the current will flow like this, which means you are pumping some base current in the transistor. Getting my point? Yes or no? Now, if base current is flowing into the transistor and sufficiently high current, what will happen to this transistor? What will be the voltage across this?
VC sat.
Yes. So something like 0.3 volts. Fine. Now, if we apply some high input over there, let us say, that's why I am saying for crude understanding, this is just for understanding we have put this transistor in this form. It doesn't mean that this is conducting, so you add 0.6 volt over here and then some voltage 0.6 volt over here, not like that. Finally, it is transistor. It is only to understand how these junctions are broken, how the current is flowing, I have drawn in this configuration. But it is transistor, all the behavior is of transistor. So once the base emitter junction is broken, this will have VC sat voltage coming across this. Any confusion in this? Any confusion, yes or no? Okay. So now let us apply some high voltage, let's say 5 volts over here, and you have 5 volts over here. Will this junction break down? Will this diode conduct or will this current flow? No, right? Because you need at least 0.6 volts more than whatever is the input to make it conduct. Understanding my point? So what will happen?
Yes,
Some
sir.
current would be flowing over here because then this junction has, because this voltage is higher. So this is kind of forward biased. That's why this is some special design for the transistor where we have the possibility for base collector current to flow. And when the base collector current is flowing over here, what would be the output at this point? Or what would be the voltage at this point?
VCC minus.
Yes. So VCC minus some 0.6. So that is ultimately 4.4 volt or 4.3, anything more than 4 volt. Understanding my point? Now here it is showing the diode behavior. So don't get confused. Simple terms, you can understand that whenever we have this transistor getting turned on, then it is behaving like a normal transistor. Whereas in the other condition, it is behaving as if there is a diode which is getting forward biased. Clear? You can ask questions.
Sir, if the input is like 4 volts, then it will be turned on, but it is still high logic, like high input.
Yes. So that is what. Now we have to go for this circuit once again. Yes, this could be even 2 volts because that is also allowed to be the high logic for the TTL. This could be 2 volts also. But now this is where our complete circuit will come into play. And that will dictate whether the transistor will be going into on or off mode. Understanding my point? This is very, very valid question. If 5 volt it's not conducting, it may conduct for 3 volt or 2 volt something. But now let us see what will happen when we go for the complete circuit, the TTL logic or TTL technology. You understood the question, right? Or not?
Yes.
Okay. So let me draw the remaining part and then let us see what happens. See, these are the questions which are there in general in our mind. D1 and then let's say Q1, R1, R2, Q2, R3, R4, Q3, Q4, D2, RL, V out. Fine, right? Now let us say the voltage is only 2 volts over here. The input voltage given over here is only 2 volts. Now let's say, see, there is possibility when you consider this in this transistor in this form, there is possibility that this junction may also break down, this junction may also break down. The only problem is when this junction breaks down, the voltage will be dropped to 0.3 volts. And when this junction is broken down, which means there is current flowing into Q2 and Q2 is turned on. Understanding my point? Yes or no?
Yes, sir.
Okay.
Yes.
Now let us say we are applying only 2 volts over here. So both the possibilities are there. Let's say if the first possibility happens, this conducts, then this is some 0.3 volts. And then the voltage appearing over here would be some 2.3 volt. And then what will happen? This transistor will break down. Because voltage is higher, of course. So Q1 will get turned on, isn't it? And so eventually Q4. Now you back calculate what voltages would appear in the circuit. Here it is 0.6. Here it is 0.6. So what will be the voltage at this point?
1.2.
Yes, 1.2.
1.2.
Because that is driving this. This has appeared, 2.3 has appeared only for the condition when Q1 is conducting. But can it conduct? The question is that, can it conduct? So now the moment 1.2 volt appears over here, the possibility for this to break down is more because there is lower voltage at this end. So now adding another 0.6 volt, what will be the voltage at this point?
1.8.
1.8. Then can this diode break down? Can it be forward biased? This is only 1.8 volt, right? What you have here, 2 volt. Can you make it forward biased?
No, sir.
No.
No,
So
sir.
our assumption was wrong. This 2 volt cannot make it work because it is dictated. The voltages are dictated by other parameters in the circuit. Understanding my point or not? Any confusion here? And this is the least possible voltage for high logic. If this cannot drive, then anything else cannot drive. Yes or no?
Yes, sir.
Yes, sir.
Up to this point you are clear?
Yes, sir.
So you have to work this circuit out in a manner. So this all is VCC. You can short it together and make it VCC common. So you have to work in this manner. You start from anywhere. Start from very crude assumption that, okay, this is conducting, fine. Then what will happen next? Once this is conducting, can this conduct? Yes. Can this conduct? Yes. Then can this voltage remain over here as whatever you have assumed? No. Then if this cannot stay at this voltage level that you have assumed, then what will happen to the middle of that voltage? That also cannot stay at the assumed value. Then that means the assumption is wrong. This is not conducting. So you start from anywhere. You will reach at the correct point if you are putting the correct values for the voltage drops which are happening. There is no current or no resistance involved calculation anywhere. This is all fixed voltage what is appearing because of the breakdown of the different junctions, PN junctions. Am I clear? Now, what is the purpose of D1? It is nothing to just to safeguard the input from any negative voltage. So this is connected like this. So as long as you are giving 0 or more than 0 volt, this is fine. There is no use for this. But the moment you give any negative voltage, let's say -1 volt, -2 volt, by mistake, of course, then this will immediately break down and it will make it 0 or 0.6. So it is only to safeguard this circuit against the negative voltages. Understanding my point?
Yes, sir.
Yes or no?
Yes, sir.
So see this circuit, whatever we have drawn, see slowly one by one we have figured out how it is evolving, isn't it? We started with this simple RTL logic, we understood the problem. Then we went for the totem pole structure and we understood that if this totem pole structure works, our problem is solved. So then immediately we went for the driving circuit. What driving circuit could be there? Now for this driving circuit, if we want to have a better way, instead of just connecting the resistance and giving the input, by that way only one input is possible, or you need to add more circuits for having multiple inputs. But this particular section, what is added over here, this gives much better flexibility. Not just one input, but you can have up to 8 inputs So this transistor, what I have drawn at the input end, this is really special transistor. It can have multiple emitters, all having one input. So this is called multi-emitter transistor. For the TTL technology, they have gone up to 8 inputs. And this is rest of the portion is same. You have only modified this transistor, and you can have A, B, C, and all that are having diode protection, of course. All these are having diode protection. Understanding my point? So this is the speciality of TTL input, that it can be expanded up to 8 inputs without modifying much in the circuit. Am I clear?
Yes, sir. Yes, sir.
So, okay, any doubts up to this point? Any doubts up to this point? Okay, so then next class we will see how to design. So what is the impact of these multiple inputs? Basically, we are realizing different gates. So NAND, NOR, and all these gates we are realizing. Then something special also, which is called AND or inverted gate, something like that, AOI. That also we will see using this kind of configuration only. So we stop the class today over here, and again tomorrow 4 p.m. that is the lab timing. So we will meet for class, and we will discuss further in the TTL and some more things in the CMOS logic, and we will close the chapter over here. Then we will go for all this minimization of the switching functions and all. Fine. So any doubt, any confusion up to this point, you may ask.